Okay, so in the last few lectures, we've gone over how to design MOS circuits and analyze MOS circuits uh, to do amplification. So in particular, we've looked at the common source, the common drain, and the common gate. And then we also said that all of these, the gain of all of these uh, circuits as a function of frequency of our signal will initially be low, and then it will be kind of reach that small signal value, and then it will decay at high frequencies. And then we came up with methods for determining this omega high and then determining this omega low. So that was basically the analysis of single stage amplifiers. Now, today we're going to actually introduce an operational amplifier, and this particular circuit, it will not involve any MOSFETs. It's just going to include a idealized version of this amplifier. And so we're mostly going to be dealing with the equivalent circuit model of our operational amplifier. We're not going to look at MOSFETs anymore. All right, so what is an operational amplifier? So an ideal operational amplifier is it has a very specific gain. So in particular, ideally, we would want the input resistance to be infinite so that no current ever flows into the operational amplifier. So an ideal operational amplifier is an amplifier where the circuit model has an RIS equal to infinity, where it behaves as an open circuit. The output resistance, it's zero, so that you don't have to share your gain between this output resistance and whatever load you connect here. Because since you have zero output resistance, everything will automatically go to the load. And same thing with this, if you have a non-ideal current source connected here, you will still get that because this is infinite, Vn will be equal to V sig, even if V sig is a non-ideal source. So that's why this is an ideal amplifier. Additionally, we're going to have an infinite gain, or a gain of negative infinity. Now, what that means is that if there is, so first of all, there is no current flowing in, no current flows in. And additionally, since we have an infinite gain, when we use these amplifiers in our circuits, we have to ensure that Vn minus and Vn plus are equal to each other. Because if there's any difference between Vn minus and Vn plus, that would make this product infinite. And so as a result, when we're looking at ideal operational amplifiers, there's going to be two governing equations. So we're actually not going to consider this. We're always going to assume that whatever voltage is at the positive terminal, or Vn plus, has to be equal to the voltage at the minus terminal. And then because the input resistance RIS equals infinite, we're always going to assume that no current ever flows out of this circuit. So of course here we would have the triangle, and then so this would be V out, and then this would be AI VI. Okay, so now based on these two rules, we can actually apply KCL and KVL to analyze operational amplifier circuits, and we're going to go over some examples in the next few slides. So let's look at an example. So let's look at this is what we call a non-inverting amplifier. And in this particular case, you have a resistor Rin and a resistor RF, and that resistor sits between the output and the VI minus. So this is VI minus, and this is VI plus. This is the input VI, and this is ground, so that's just 0. And then this is V out. Okay, so the first thing we know is that no current flows into here. And we also know that since this is VI, this has to be equal to this voltage. So you have that VI equals VI plus. Here, I'm going to call this Vn just to, which is also has to be equal to Vn, VI minus. So as a result, now we know what Vn is. So now let's compute the gain. So we know that this voltage is going to have to be VI. And then we could do this nodal equation. So we have that VI minus 0 over Rn plus, remember there's 0 current flowing through here. And then we have one more branch, VI minus V out over RF has to be equal to 0. Okay, so I can just basically manipulate this equation, solve for V out over V in, and I'm going to get basically that 1 over R in plus 1 over RF V in equals V out over RF. So I just moved this to the other side, and I factored out the 1 over RF and 1 over R in, and that's going to give me that V out over V in, or the gain of this particular circuit, is actually 1 plus RF over Rin. So that means that if I can choose the ratio of the input and RF, so of these two resistors, to choose my gain. So for example, if I choose them all to both to be 1 kilo ohm, I'm going to get a gain of 2. If I choose Rin to be 1 kilo ohm and RF to be 10 kilo ohms, then I'm going to get a gain of 11, and so on. So I can actually use this operational amplifier to realize whatever gain I would like to realize. All right, so this kind of summarizes the formulas I derived in the previous slide. So now let's go. Okay, so this is what we call a differentiating amplifier. And in particular, we know that here we have a capacitor. And for a capacitor, we know that the current going through that capacitor is equal to the capacitance times the time derivative of the voltage drop across that capacitor. And so for this particular case, we're going to have to use that when we apply KCL. But before we do, since the voltage here has to be the same as the voltage here, now we know that the voltage there has to be 0 because this voltage is 0. Additionally, no current flows into either terminal. So if we apply KCL at this node, what we're going to have is for the capacitor, we have C in times ddt of the voltage drop, which is 0 minus V in, plus 0 minus V out over RF. And that has to be equal to 0. And so now we can solve this equation for V out, and what we will get is actually that V out equals RF C in, and then a negative sign d dt of V ins of t. So that's basically our differentiating amplifier, and that's the gain. So let's look at an example of this equation. So let's assume that RF equals 1 mega ohm, and then Cin equals 1 microfarad. I chose those so that the product would be 1 to make my life easier. And let's just assume that Vn of t equals sine of 10t. So what that would mean is that V out is actually equal to negative 1 mega ohm times 1 microfarad. And the mega is 10 to the 6, micro is 10 to the negative 6, so that's just negative 1. d dt of sine 10t. And so this just gives me negative. And then that derivative is just cosine 10t times 10. So I get that this is actually just equal to negative 10 cosine 10t. So I hope this makes sense. Now let's look at a more complicated example. Let's say that instead of, if I were to tell you that, so let's just go back. Let's say I didn't give you the input and I gave you the output. So I told you that V outs of t was actually going to be equal to let's just say t. And I asked you what is V in. Well, you would actually have to do and I also told you that V outs or V ins of 0 equals 0. So you have V ins of t here. So now you could actually just plug in here t. And so now what you have to do is integrate both sides of the equation so that you're going to have the integral from 0 to t tau d tau equals v negative v ins of, here, I'm not going to skip steps. So negative the integral of d dt of v ins of t of tau d tau dt 0 to t. And remember, we have to introduce a dummy variable because you can't have an integral over time. This should be d tau, sorry. Now this here is just actually equal to v ins of t. Sorry, I need to put a negative sign over everything. So negative minus v ins of 0. And then we know that v ins of 0 is 0. And then this is just actually equal to t squared. And so then I get that this is just equal to negative v ins of t. So now we have that v ins of t actually equals negative t squared. So if I gave you kind of 3 of them, you would be able to now solve for v out, but you need to know what the input is. All right, so those are just some numerical examples, but before we move on from this slide, let's just look at one more thing. So the reason this is called the differentiating amplifier is because the way that the input and the output are related are through differentiating. So let me just go back here. So if you look here, the output is just the derivative of the input. So if I put in here t squared, I get here some constant times t squared. I'm going to get some other constants, so C1, times t times 2t. And then if I put in a cosine here, then I'm going to get a negative sign, and so on, because effectively this amplifier is taking the derivative of the input. So that's why it's called the differentiating amplifier. Okay, let's look at another example. Yeah, so here's the derivation again for your reference. So remember that this is just the C d dt of V, where this is the voltage drop across the capacitor. And we're going to be doing this a lot more in the next few lectures, so it's good that if you get comfortable with that now. All right, let's continue. Okay, so now let's look at what we call a differential amplifier. So first thing to note here is that if you look at this branch here, since no current flows through here, whatever current flows through this resistor has to flow through this resistor. And so this is just a voltage divider. And so a total of Vs2 has to flow through these two resistors. And because the resistances are the same, we automatically know that this is just Vs2 over 2. Additionally, we also know that this voltage has to be the same as this voltage, and so that means that this voltage is actually Vs2 over 2. And now this allows us to basically solve our circuit. So we can apply this nodal equation. So we're going to have we can look at all the currents coming out of here. So we have Vs2 minus Vs1 divided by R. So in particular, we have Vs2 minus Vs1 divided by R. So that's a current going this way. Additionally, a current going that way would be Vs2 minus V out divided by R, Vs2 over 2 minus V out over R. And since there's no current here, those are all the branches, so we have that all the currents have to sum up to 0. And then what we can do is now solve for V out, so we're just going to move this to the other side. And we're going to get that V out over R equals Vs2 over R minus V out plus, oh yeah, so there should be Vs2 over 2 and Vs2 over 2 over R. And you could already see that the R's cancel in the numerator, and then you end up with V out equals Vs2 minus Vs1. So this is called a differential amplifier because it takes, because it takes the difference between the two. Actually, this is not called a differential amplifier. I forget what this is called. So that's not, I forget what this is called, but in your book, you can actually look what this is called. But in particular, it's taking the difference between the two input terminal signals. Okay. So let's go ahead and look at another example. All right, so this is actually a common type of problem that we would give in an exam. So why don't you spend a few minutes trying to solve it, and then we can come up with an equation for the gain. It's actually a differential amplifier like the one we went over a couple of slides ago. I will go over it in the next few seconds. In particular, you can assume that to find an equation of the gain, first thing you need to realize is that the current flowing through here, I, is 0, which means that no voltage drops to this resistor, so that this is 0 volts, which means that this is also 0 volts. And then what that leaves you with when you apply, you have zero current going through here. So when you apply KCL here, you're going to have 2 microfarad ddt of 0 minus V in, so of t, plus 0 minus 3 sine t, 0 minus 3 sine t, divided by, so this is actually V out of t, 500 kilo ohm, and that should also add up to 0. So at this particular point, that's to find the equation for the gain, or to find the actual voltage V in. We need to basically multiply by 500 kilo ohms, top both sides of this equation, so that this kilo ohm disappears, and then the 2 micro times the 500 becomes a 1. So we end up with basically negative ddt V ins of t equal plus negative 3 sine t equals 0. Okay, so let's continue with this. Okay, so in the previous slide, we got to this point where we said that and V out was actually 3 sine t. So in the previous slide, I basically wrote negative ddt of V ins of t minus 3 sine t equals 0. Well, this is actually just V out. So if I move this to the other side, then I get that equation there. Now I need to basically determine what V in is. So to find what V in is, assuming that V in of 0 equals 3. So first we need to figure out what V ins of 0 is, which is what I gave you in the previous example. So we integrate both sides of the equation. And that's going to give us V ins of t minus V ins of 0. And then this is going to give us from 0 to tau, from 0 to t, V out d tau. So we can actually integrate this equation. So the integral of this is negative cosine t minus plus cosine 0, which is actually going to give us 1. So we're going to have V ins of t minus V ins of 0, which we said was 3, is equal to negative, so cosine t plus 1 minus 3, so minus 3, so there should be a 3 here. So the two negatives become a positive, and then you have plus 3. And so then you get that V ins of t actually equals to cosine t times 3. All right, so this is something you should be able to solve for your exam. These kinds of questions is fair game for an exam. All right, so let's look at another. Okay, so here's kind of the answer. Now let's go ahead to the next slide. All right, so here's kind of a more interesting circuit. So as you can see, the underlying principle is always the same. I figure if I know the voltage on one branch, I automatically know it on this branch. So it's going to be 0. So VA is actually 0 because the positive terminal is grounded. It's telling me the next thing I'm going to do is that I'm going to assume that no current flows into the input terminals. So that means that it's easy to apply KCL at the node. So I'm going to apply KCL at that node A. So I have basically 0 minus VI over R1 plus R0 minus Vx over R2 equals 0. And I'm trying to find V out, so I need another equation, but then I can apply KCL at Vx. So I have Vx minus 0 over R3 plus Vx minus 0 over R2 plus Vx minus V out over R4. That has to be equal to 0. So I just have these three currents. Now you can see that V out as a function of Vx is just simply equal to R4 times 1 over R3 plus 1 over R2 plus 1 over R4 Vx. And this gives us that Vx is just equal to R2 over R1 Vi negative. So I can just substitute this thing here to the -1 for Vx. So I'm going to get basically, if I can rewrite this equation down here. So basically I'm going to get that, well, yeah, so I'm going to get that basically R4 times 1 over R2 plus 1 over R3 plus 1 over R4 to the -1 V out equals -R2 over R1 V in. And then I can divide both sides, multiply both sides by this factor to get that V out over V in is just equal to -R2 over R1 R4 1 over R2 plus R1 over R3 plus 1 over R4. So I hope that at this point you're kind of getting the pattern of how you solve these op-amp circuits. So that's the gain for this one. Now let's kind of go through it. So like I said earlier, whatever voltage you have here is the same voltage you have here. Check. When you apply KCL, you have effectively two currents because this current is 0. So that's why you have the two currents. That gives you the gain. You apply KCL at this node, you will get this equation. And then finally, when you combine the two equations, you're going to get that that's the gain. And in this particular case, I multiplied it out. All right. Okay, so let's look at another example. I think I have a couple more and then we can call it a day. This is similar to the one before. One thing to note here is that even though there's this resistor here, because the input resistance of the amplifier is infinite, or it's an open circuit, there's still no current I going through here, which means that no current flows through here. And so whatever voltage is here is also the voltage here, which is 0 volts. Additionally, we know that that voltage has to be the same as this voltage. And finally, we know that the voltage Vc has to be equal to the current flowing through has to be C ddt of the voltage flowing through the capacitor. Now, because of the way the terminals are labeled here, that would imply that there's a current flowing from here to here. Sorry. And so as a result, here we would just have basically VC. Okay, so we can basically now look at what, write out our equation for this particular circuit. And what we're going to have is, so this voltage here is 2V, 2 cosine t. And we know that this voltage here is 0, so we're going to have that 0 minus 2 cosine t d dt times c plus the 2 mega ohm, and then in the numerator we would have 0 minus V out. 0 minus V out, or VO. That should be equal to 0. And then we also have that the capacitance is 1 microfarad, so I'm just going to plug in 1 microfarad here. And I can move this to the other side and multiply by 2 mega ohm so that I can get that V out equals 2 mega ohm times 1 microfarad. Of course, the mega cancels the micro, times the time derivative of cosine times negative 2. The time derivative of cosine is sine. So wait, negative sine t. And so that's going to give me that V out equals, this cancels this, so that's just 2, 4. So we have 4 sine t. Cool. So that's another example of a circuit. So as you can see, most of these are pretty simple. You just apply KCL and they kind of break down. Now we're going to look at a more complicated example. So in this particular example, what we have is 3 amplifiers. Now the reason I'm going over this one is because, as you will see, to analyze more complicated circuits, what you typically do is you divide and conquer. So what we're going to do is we're going to start by just analyzing the top circuit to figure out what the voltage would be here. And then we're going to analyze the bottom circuit to figure out what the voltage would be here. And then those will be the inputs to this third circuit, which will lead us to the final gain. Okay, so what we have here is that, so the first thing is, what is the voltage at the non-inverting terminals of A1 and A2? So if you look at this one, VI2 is connected to the plus terminal, so we know that this has to be VI2. And then we have that VI1 is connected to this terminal, so this has to be VI1. So basically, VI1 would be the voltage at terminal A1. Okay, cool. So now, if we were to look at just the top circuit, what we have here is, we know that this is going to be VI1. And then we could do this node equation. And what that's going to tell us is that VI1 minus 0, which is the voltage here, divided by R1, so that would be IR1, plus VI1 minus VO1 divided by R2 have to be equal to 0. So that would be this one. And then we can solve for the ratio of the VI to V out. by simply moving all the V out terms to the other side. And so what we're going to get is actually 1 over R1 plus 1 over R2 times VI1 equals V out 1 times R2. So we move this term to the other side, and then we multiply by R2. And so that's going to give us what V out is in terms of VI. Okay, so here I wrote that more cleanly. And so we got this particular gain. Now, if you would have looked closely, this is actually what a configuration that we already studied called the non-inverting configuration. So we could have also just recognized that this circuit is the same as the one in the textbook here, and just directly use this formula to get the gain up to V out 1. Okay, so now we can look at the second circuit, and what you can recognize here is that this is also a non-inverting amplifier, so you have here VI2, and so you can basically say that the gain will actually V out 2 will actually just be in this particular case, so R2 over R1 plus 1 VI2. And yeah, so of course you could have done KCL to say that basically VI2 minus 0 divided by R1 plus VI2 minus VO2 divided by R2 equals 0. Then you move out the VO2 to the other side and multiply by R2, and what you end up with is this equation here. All right, so now that we have the gain for those two, now we know what VO2 is in terms of VI2. So that's this equation here. So now we actually end up with this new circuit where the two inputs to the new circuit are now these, VO1 and VO2. And so now we can actually analyze the rest of the circuit. Now, since no current flows through here, remember that one of the properties of the transistors is that zero current flows into the input terminals. What that means is that whatever current flows through this terminal has to flow through this terminal. And to figure out what this voltage Vx is, we can basically do a voltage division. So we know that basically Vx is going to be equal to Vx will be equal to VO2 divided by R3 plus R4 times R4. And so we know that that's the voltage here and that's the voltage here. Additionally, we could do KCL in this particular node, and we're going to have basically Vx minus VO1 divided by R3 plus Vx minus VO divided by R4. And that has to be equal to 0. Okay, so at this point, we can actually move the VO to the other side. And then we will actually have that, yeah, so, and multiply by R4. So we're going to have VO equals R4 over R3. And then we're going to have here Vx plus Vx, sorry. sorry, so R4, and then we're going to have here 1 over R3 plus 1 over R4 Vx minus VO1 divided by R3 times R4. So I just rearranged the terms a little bit. I can rewrite this factor by finding a common denominator. So I'm going to have R3 times R4, or sorry, R3 plus R4 divided by R3 times R4. So basically I found a common denominator and I get that new factor. And now something magical will happen because when I plug in this expression for Vx, we already see that the R3 plus R4 cancels the numerator term. So now we're going to get that V out equals R4. And then we're going to have Vx, which is basically R4 Vx O2 divided by R3 times R4 minus R4 over R3 VO1. And then you can see here that the R4s will cancel in the numerator and denominator. And so I actually get that my gain is actually R4 divided by R3 VO2 minus VO1. Okay, so let's continue with this. So that's what I just did, solve for VO in terms of VO2 and VO1. So we got that actually, VO was actually R4 over R3, VO1 minus VO2. VO2 minus VO1. Yeah. And then finally, we can actually replace VO2 and VO1 with basically with our original expressions, which basically said that VO2 is equal to 1 plus R2 over R1 VI2, and VO1 equals 1 plus R2 over R1 VI1. So when we do that, we get that the two gains multiply each other, and then these are the original inputs. So what we've actually just analyzed is what we call an instrumentation amplifier, and this is used in experiments when you need to amplify a very small signal. In particular, this scenario actually has a very good signal to noise ratio and a common mode rejection, so meaning that it looks at the difference between two terminals and it amplifies it very big while suppressing kind of the average of the two signals. Now the reason why you would want to do that is because if you have a small signal you're trying to measure in a noisy environment, you would basically probe the system here, and then you would probe the system here, and then you want to see the difference between what happens here and here. Well, your noise would be common to both terminals. So by amplifying that difference, you're actually isolating the effect of what's going on in between. Yeah, so this is actually a fairly important amplifier, but now you know how to analyze. But I wanted to show you this more so that you knew how to analyze more complicated systems. Okay, so that's actually all there is for this lecture. Next lecture, we're actually going to look into non-ideality of operational amplifier circuits, and then and a few more examples. So I'll see you next time.